So before going for pKa and pH, we will first revise some important theories of acids and bases. Okay. So first important theory for defining acid and bases is Arrhenius theory. So according to this theory, Arrhenius acid is any substance that releases hydrogen ion in water. Means Arrhenius theory is related to water, dissociation of acid into water, okay, in aqueous solution. So acid is any substance that releases H plus ion in water is acid. Okay, examples are hydrochloric acid, hydrogen cyanide, HNO3, H2SO4, etc. All these releases H plus ion in aqueous solution. For example, if we see the reaction of HCl and in water, means when HCl dissolved in water, it dissociates to give H plus and Cl minus ion. Okay. According to this theory, base is any substance that gives the hydroxide ion when it dissolves in water. Okay. For example, if we consider sodium hydroxide, potassium hydroxide, calcium hydroxide, these substances when dissolved in water produces OH minus ion. So these are considered as base according to Arrhenius theory. Now another important theory of acids and bases is Bronsted-Lowry theory. So according to this theory, acid is considered as proton donor, means any substance that can donate a hydrogen ion, that is proton, in a chemical reaction is called as acid according to Bronsted-Lowry theory. For example, again HCl, HNO3, H2SO4, these are considered as acid because they can donate proton in a chemical reaction. And according to Bronsted theory, base is considered as proton acceptor. That means any substance that can accept a hydrogen ion in a chemical reaction is called as base. Example, OH minus. So according to Bronsted theory, OH minus ion is considered as base because it can accept proton. Similarly, ammonia molecule can accept proton, so it is considered as a base. Okay. So for example, if reaction between HCl and ammonia takes place, HCl acts as proton donor, so it is considered as acid, while ammonia acts as proton acceptor, so it is considered as base to form ammonium ion and chloride ion. So according to Bronsted theory, there is one more concept, that is conjugate acid-base pairs. So according to Bronsted theory, conjugate base is when an acidic substance loses a proton, it forms a base called as the conjugate base of an acid. So if an acid is strong acid, then its conjugate base is a weak base. For example, chloride ion is the conjugate base of hydrochloric acid. Okay. So in reaction of HCl with water, acid donates proton to water and forms hydronium ion, and remaining portion of acid, that is Cl minus, becomes the base. So it is considered as conjugate base of HCl. Similarly, conjugate acid is when a basic substance gains a proton, it forms an acid called the conjugate acid of the base. So conjugate acid is a species which is generated by accepting the proton by the base. So base accepts proton and converted to acid called as conjugate acid. Now if we consider strength of acids and bases, according to Bronsted-Lowry theory, strength of acid depends upon its tendency to give up the proton. Because according to Bronsted theory, acid is a substance that donates proton in a chemical reaction. So more easily the acid donates proton, the stronger is the acid. Similarly, strength of base depends upon its tendency to accept proton, because we know that According to Bronsted theory, base is a proton acceptor. So more readily it accepts proton, stronger is the base. For example, if we consider reaction of sulfuric acid with water to form H3O plus and HSO4 minus, or reaction of HCl with ammonia. In these two reactions, sulfuric acid and hydrochloric acids are strong acids because they tend to give up a proton very readily. We know that H2SO4 when added to water immediately it releases proton. Similarly, when HCl reacts with ammonia, it releases proton to form NH4 plus ion, and thus sulfuric acid and hydrochloric acid are strong acids. Conversely, the conjugate base obtained from sulfuric acid, that is bisulfate anion, and conjugate base obtained from HCl, that is chloride ion, are weak bases since they have little tendency to hold on proton. So strong acid generates weak base. So H2SO4 and HCl are strong acids. So their conjugate bases, bisulfate ions and chloride ions, are weak bases. Now if we consider reaction between ammonia and water, ammonia is a very weak base while water is very weak acid, and so the conjugate acid of ammonia, that is ammonium ion, is stronger acid, and OH minus, which is a conjugate base of water, is a stronger base. So the stronger an acid, the more easily it loses a proton. So strong acid undergoes essentially complete ionization in a solution. So we can consider the strength of acid as a high when it undergoes complete ionization. Consider this hypothetical reaction that HA is any strong acid, which releases H plus ion and donates it to water to form A minus, that is conjugate base of acid HA, and H3O plus ion, hydronium ion. If this reaction occurs to give complete ionization, then HA considered as strong acid. Inorganic acids are strong acids. For example, HCl, H2SO4, HNO3. This mineral inorganic acid dissociates completely in water, so they are strong acids. For example, if we consider reaction between HCl and water, this arrow indicates that HCl dissociates to large extent in water. Means the reaction of rate of forward reaction is higher than backward reaction, as it is a reversible reaction. So HCl is strong acid because it dissociates almost completely in water. Now if we consider weak acid, it is only partially ionized in a solution. So strength of acid depends upon ionization. For example, consider any weak acid. If the acid is not completely ionized, it is partially ionized in water, then acid is considered as weak acid. In this reaction, rate of backward reaction is higher than forward reaction, means more amount of unionized acid will be present in this solution. So it is considered as weak acid. For example, carboxylic acids are weak acids. Example, carbonic acid, acetic acid, and many other organic acids. If we consider reaction of carbonic acid with water to form bicarbonate ion and hydronium ion, the carbonic acid dissociates slightly, partially in water, so it is considered as weak acid. Same as that of acids, base strength also depends upon its ionization. A strong base is completely ionized in a solution. consider the reaction between any base like BOH in water. If there is complete ionization of base takes place, then the base is considered as strong base. Example of strong bases are inorganic bases like sodium hydroxide, potassium hydroxide, calcium hydroxide, etc. We know that NaOH, when dissolved in water, it dissociates completely to give Na plus ion and OH minus ion. Okay. So NaOH exists into ionic form in aqueous solution, so it is strong base. A weak base is only partially ionized in a solution. Okay. If we consider the example where the base is not completely ionized, means maximum portion of base remains in unionized form, then the base is considered as weak base. For example, ammonia, amines, these are weak bases. For example, if methylamine is dissolved in water, it will dissociate very slightly to give ammonium ion and hydroxide ion. So methylamine is considered as a weak base. The strength of acid can be expressed in terms of acidity constant and pH. These are the two terminologies that are used to indicate the strength of an acid. It is acidity constant and pH. So let us see what is this acidity constant or ionization constant. An equilibrium constant of a reaction reflects how far the reaction proceeds towards completion. And we know that equilibrium constant, equivalence, is equal to molar concentration of product divided by molar concentration of reactant. Now we will see what is acidity constant. An equilibrium constant for ionization of acid in water is called as acidity constant, which is denoted as Ka. For example, consider the example ionization of acetic acid. When acetic acid is dissolved in water, it dissociates very slightly in water. Maximum amount remains unionized to form acetic acid, dissociate to form acetate ion and H plus ion or H3O plus ion. So equilibrium constant for this forward reaction is concentration of acetate ion into concentration of H3O plus ion divided by concentration of acetic acid, that is unionized species, into concentration of water. Now in this reaction water exists into excess amount, so the change in the concentration of water is not much significant, so we can consider the concentration of water as a constant. So this K equivalence is also a constant and concentration of water is also a constant. So K equivalence into concentration of water, this becomes a constant, and this constant can be named as Ka value, that is acidity constant. So according to this reaction, Ka acidity constant is equal to concentrations of ionized species upon concentration of unionized species. Okay. So from this equation we can say that more ionized an acid, means if concentration of ions products are more than concentration of reactant, then the value of Ka will be large and the acid is considered as strong acid. So more ionized an acid, larger is the value of Ka and stronger is the acid. Now the terminology used to indicate Ka value is pKa, or indicate the strength of acid is pKa. pKa is the negative logarithm of Ka value. As it is a negative logarithm, as the Ka value gets larger, pKa gets smaller. So pKa is negative log of Ka value. Smaller the pKa value, the stronger is the acid, because When Ka gets larger, pKa gets smaller. So more the ionization of acid, more will be Ka value and smaller will be the pKa value, and the acid is considered as strong acid. Let us see some examples. HCl, H2SO4 are considered as strong acids because they have very small pKa value. Phosphoric acid is moderately strong because it is having slightly higher pKa value than HCl and H2SO4. While organic acids like formic acid, acetic acid, these are considered as weak acids because their pKa is further increased. Water is considered as very weak acid because it has a high pKa value, that is 14. Now another terminology which is used to define concentration of H plus ion, OH minus ion is ionic product constant for water. The pure water which ionizes to small degree, and this self-ionization of water produces positively charged hydronium ion and negatively charged hydroxide ion. Okay. So in this way water molecule reacts to form hydronium ion and hydroxide ion, or this reaction can be written in this way, that water molecule dissociate to give H plus ion and OH minus ion. The equilibrium constant for this self-ionization of water is referred as ion product for water, and it is indicated by the symbol Kw. Okay. So Kw, ion product for water, is equal to concentration of H3O plus ion into concentration of OH minus ion, or it can also be denoted as Kw is equal to concentration of H plus ion into concentration of hydroxide ion. So we know that at 25 degrees Celsius the value of Kw is 1 into 10 raised to minus 14. Therefore, concentration of hydronium ion into concentration of hydroxide ion becomes 1 into 10 raised to minus 14, or concentration of H3O plus is equivalent to concentration of H plus ions generated in the water. So we can denote as concentration of H plus ion into concentration of OH minus ion is equal to 1 into 10 raised to minus 14. And in pure water, concentration of both the ions are equal. So therefore concentration of H3O plus or H plus ion is equal to concentration of OH minus, and both equal to 10 raised to minus 7, or we can denote it as concentration of H plus is equal to concentration of OH minus, which is equal to 10 raised to minus 7. Now another terminology which is used to indicate the strength of acid is hydrogen ion concentration or pH value. The concentration of hydronium ion and hydroxide ions in aqueous solution are usually smaller than 1 molar, and the logarithms of these concentrations are negative numbers. Therefore, Sorensen introduced a practical concept of expressing acidity as the negative logarithm to the base 10 of the hydronium ion or H plus ion, and concentration called as pH. So pH is the negative logarithm to the base 10 of H plus ion concentration. Thus the pH is the negative logarithm to the base 10 of H3O plus or H plus ion concentration. Similarly, pOH is the negative of the logarithm of the OH minus ion concentration. Now we know that at 25 degrees Celsius, ion product of water is equal to concentration of hydronium ion into concentration of OH minus ion, and it is having value of 10 raised to minus 14. So if we take the negative logarithm of this equation, it becomes negative logarithm of Kw equal to negative logarithm of H3O plus negative logarithm of OH minus, that is equal to negative logarithm of 10 raised to minus 14. Now negative logarithm of Kw is given the symbol pKw. So pKw is becomes equal to pH plus pOH, which is equal to 14. So pOH is equal to 14 minus pH, means sum of pH plus pOH for any solution is equal to 14. So when solution is neutral, then concentration of pH, means concentration of H plus and concentration of OH minus are equal. So pH is equal to pOH, which is equal to 7 at neutral pH. So depending upon the concentration of pH and pOH present in the solution, or H plus ion concentration and pOH minus ion concentration present in the solution can be classified as acidic, basic or neutral. So consider this condition in which when concentration of H3O plus hydronium ion or H plus ion is greater than concentration of OH minus ion in a solution, then the pH at this stage will be less than 7 and the solution is termed as acidic. So when concentration of H plus ion is greater than OH minus ion, solution is acidic and pH becomes less than 7. When concentration of H3O plus and concentration of OH minus ion are equal, the pH will be 7 and the solution is considered as neutral. And in another situation where concentration of H3O plus is less than concentration of OH minus, then pH will be greater than 7 and the solution is considered as basic. Let us see some examples. So the pH scale, Sorensen's pH scale includes range of values from 0 to 14 that describes the acidity or basicity of a solution. For example, so this scale from pH 0 to 14, it is considered as Sorensen's pH scale. So when the concentration of H plus ion is higher, the pH is very small and solution is considered as acidic. Okay. So as the concentration of H plus ion increases, the value of pH decreases and the solution is said to be becoming more acidic. So as the concentration of H plus ion increases, pH value decreases and acidity increases. At neutral pH, the concentration of both H plus and OH minus is equal and pH is 7 and the solution is neutral. As the concentration of H plus ion decreases, the pH value increases and solution becomes basic. Okay. So as the pH value increases, basicity of the solution increases. So smaller the pH, stronger is the acid, and larger the pH, it will be basic solution. You can refer the books for this topic. Thank you very much.